Hello everybody. In this lecture, we are going to see Lagrange's theorem in abstract algebra. This theorem stated relation between order of a finite group and order of their subgroups. The statement of Lagrange's theorem is that if H is a subgroup of a finite group G, then order of H divides order of G. But you know what? The interesting story behind Lagrange's theorem is that actually Joseph Lagrange, he's belonging to France, did not prove this theorem. Actually, Joseph Lagrange stated something about number of distinct polynomials in n variables and permutations of these n variables. He stated this statement in his article, Reflections sur la Resolutions Algebraique des Equations. We are giving the reference for this article, which was published in 1771 from Berlin. So what was his statement? So let us understand first what actually Joseph Lagrange stated in his article in 1771. So for the sake of simplicity to understand his statement, consider three variables x, y, z. So let x, y, z be the three variables. You may take n variables. So now for the simplicity, I am considering three variables x, y, z be three variables. All right. Now we know that according to theory of permutations, how many ways you can arrange these three variables. That means number of possible permutations in x, y, z are it is nothing but 3 factorial, that is equal to 6. All right. Now we will define a function in these three variables. So suppose I am defining P1 is a function with these two variables x, y, z. Now I'm considering one simple function. So I'm considering, suppose, a polynomial of these three variables. Now I'm defining polynomial as x minus y minus z. All right. Now now I will construct the permutation functions using these three variables. So now I will construct another polynomial P2, which is again a polynomial in three variables. Now keeping x as it is, minus z minus y. Now another third one polynomial I am generating by using the permutations in x, y, z. So y minus x minus z. Now P4, again it is a function of three variables, that is y minus z minus x. Fifth polynomial, that is z minus x minus y. And the last sixth polynomial I can write as z minus y minus x. Now I have constructed these 6 polynomials using one polynomial that is given, that is P1. But if we observe these 6 polynomials, now just see these two polynomials are equal. That means P1 is equal to P2. These two polynomials are same. Therefore, P3 is equal to P4. And these polynomials are also giving the same answer. Therefore, P5 is equal to P6. That means after permutation of the polynomial, I got only 3 distinct polynomials. All right. And therefore, number of distinct polynomials, number of distinct permutate polynomials is equal to, that is 3. And what actual stated by Lagrange, That is, the number of distinct polynomial always divide the total possible permutations of these variables. So total possible permutations of x, y, z are 6 and the total distinct polynomials are 3. 3 divides 6 and therefore this result on polynomials stated by Joseph Lagrange in 1771. But this result on polynomials after that extended to the finite permutation groups by Camille Jordan in 1861. Then after that, so many developments has been done later on in abstract algebra, and hence finally this general theorem on finite groups bearing name as Lagrange's theorem. So let us see what is Lagrange's theorem in abstract algebra. So to understand or to learn Lagrange's theorem in abstract algebra, first of all we will see something terminologies cardinality and order. So usually number of elements in set is called as cardinality of that set. So suppose A is a set having 3 elements A, B, C. So the cardinality of A is equal to 3. The notation of cardinality is like that. But instead of only set, if I am considering algebraic structure, that means set with binary operation, and that algebraic structure will satisfy some axioms like group, then the number of elements in that algebraic structure is called as the order of that structure. And therefore number of elements in group is algebraic structure is called as order of group. Suppose G is a group containing 3 elements A, B, C with some binary operation, then the order of G is equal to 3. So this is a very basic difference between cardinality and order. Right? Now we are ready to prove Lagrange's theorem. So first of all, we see the statement of the Lagrange's theorem in abstract algebra. If capital H is a subgroup of a finite group G, then prove that order of H divides order of G. So let us prove this theorem. Now we will prove this theorem by using coset theory. So just I am proving this, so I'll write proof. So read the statement. H is a subgroup of finite group G. But we know that every group has trivially some subgroups. We know that singleton E and group itself is a subgroup of itself. And therefore, these subgroups, which are always subgroup, that means singleton E and group itself, both are subgroup of G, and these subgroups are called as the improper subgroups. That's why first we will see whether this theorem is true for improper subgroups or not. So in case number one, suppose that if H is improper subgroup of G, improper subgroup of G. All right. Okay. That means H is either singleton E or H is equal to G itself. All right. Now G is a finite. So let us consider the order of G is n. So let order of G is equal to This is the order of G is equal to n, and therefore if you see order of H is equal to 1 here when we are considering singleton set E, and if H equal to G, then order of H is equal to order of G, and that is nothing but n. So in both the cases, this 1 is always divides n, and the n itself is divides n. So in this case, when H is the improper subgroup of G, the order of H divides order of G. So theorem is true, or theorem is proved when H is improper subgroup. But the interesting thing is we want to show that this theorem is also true for proper subgroup. So now I'm considering case number 2, and in this case I'm supposing that H is a proper subgroup. So suppose H is a proper subgroup of G. Proper subgroup of G. Right? Now already we have assumed that order of G is equal to n. Now this is a proper subgroup, therefore I am considering its order. So let order of H is equal to something which is less than n because it is a proper. So I am denoted that order say m. So let order of H is equal to m. Now we'll prove this case by using concept of cosets. All right. Since the order of H is equal to m, what is its meaning? Meaning is the set H containing m distinct elements. So I'm considering let H containing m distinct elements, H1, H2, and the last element will be Hm. These are the m elements. Now to construct coset of this H in G, we have to take any element from the group G. So let any element G, small g, belongs to this group capital G. And now I'll construct right coset of H and G using this element G. Therefore HG, this is a right coset of H, is nothing but H1 into G, comma, H2G, comma, dot, dot. The last element is Hm into G. Now after construction of this right coset of H and G, one question arising in my mind, and that is the cardinality of this coset Hg is m? I'm guessing that, of course, yes, its cardinality is m. That means, in my mind, I'm thinking the cardinality of Hg is equal to m. But we have to show it. To show this, we will construct another coset of H, and to construct that coset we need one more element from the group, and this is a group, that means definitely it has identity, right? That's why I'm considering another element E, that is the identity from G, for the construction of another coset. So since G is a group, therefore identity E belongs to G, and therefore right coset HE is equal to H1E, H2E, and HME. And it is nothing but, according to identity law, it is nothing but H. All right, and therefore HE is equal to H, and hence the cardinality of HE is equal to cardinality of H, and we know that the cardinality of H, or degree of H, is equal to what? M. And hence we can say that the number of elements in the right coset He are m. Now we know that there is one-to-one correspondence between any two right cosets of H in G. This lemma we have proved. And therefore, the number of elements in this coset are equal to number of elements in this right coset. Therefore, according to that lemma, what is that lemma? There is one-to-one correspondence between any two right cosets of H in G. It means cardinality of every right coset of H in G is same, and therefore the cardinality of this right coset Hg is equal to cardinality of this right coset, and it is nothing but m. And hence we have proved that the cardinality of Hg is equal to m, and that's why this right coset Hg containing definitely m elements. All right. Now, what is the order of G? The order of G is equal to n. So, can you predict that using n elements of G, how many distinct cosets of H in G can be constructed? I know that. You are thinking that since order of G is equal to n, so we will be getting n distinct cosets of H in G. But also we know that distinct right cosets creates equivalence class, so they provide partition of G. Right. So if I'm thinking that since the order of G is equal to n, by taking one by element from G, I'm constructing n distinct cosets. So suppose Hg1, Hg2, and last finally Hgn be n distinct cosets of H in G. Right? Now, we know that distinct right cosets of H creates equivalence class, and hence they provide partition of G. Therefore, this G we may write as a G is equal to union of these distinct right cosets. That means Hg1 union Hg2 union, carry on like this, and the finally union of Hgn. Now I will take the order of left side. Order of G is equal to cardinality of first coset plus cardinality of second coset plus cardinality of last coset. And we know that order of G is equal to n. The order of this coset, right coset, is m. So m plus m plus m, how many times? N times. So it is n times. Therefore, we can write n is equal to m times n. And therefore, after cancellation of this n, I will get m is equal to what? 1. But m is 1 means order of H is 1. Order of H is 1, it means that H containing only one element, that is identity, and it is improper subgroup. But already in the second case, we have assumed that H is improper subgroup. That means definitely m is not equal to 1 and m is not equal to n. What is its meaning? Its meaning is H H generates or H gives some less than m right cosets. All right, and hence H so number of distinct right cosets of H in G, right cosets of H in G are less than m. Say say less than m, less than m, less than m, say k. K is an integer less than what? M. And therefore, let hg1, hg2, and hgk be k distinct right cosets. Distinct right cosets of h in G. We know that distinct right cosets of any subgroup of G creates equivalence class, and they provide partitions of G. Therefore, G can be written as union of these distinct right cosets. All right, union of finally GK. Now, what is the order? So order of G is equal to cardinality of the first right coset plus cardinality of the second right coset, and continuing this summation up to cardinality of HGK. We know that this right coset containing m elements, so order of G is equal to n. So this is m plus m plus m. These are the k cosets, therefore it is k times. So m plus m k times, therefore we are getting n is equal to m k times, means m into k. And therefore n divided by m is equal to k. What is k? K is an integer. We know that when any number divided by any other number, and if we got answer as an integer, it means this number perfectly divides n. So this implies m divides n. So what is the m? M is nothing but order of h divides order of G. And this is the end of Lagrange's theorem. So we have proved Lagrange's theorem by using coset theory. Now we will see some applications of this Lagrange's theorem. So see the application 1, that is also theorem. If G is a finite group and if A belongs to G, then prove that order of A divides order of G. Now, in this theorem, the new thing is order of elements. So, first of all, we'll discuss what is the meaning of order of element. So, order of element means I'm considering, see, A is element from group G. G is a group, that means it has binary operation, some binary operation, star suppose. Now I'll take A star A. So according to closure property, this product A star A is also belongs to G by closure property. All right. Now continuing in this way, that means this is denoted by A square, suppose. Now A square into A, that is A cube, also member of G. So we are doing like this continuously. Then after some time, I may get A to the power some number, suppose M, and it is equal to E. So first time when I have started multiplication A with itself, I got A multiply or A star A M times, and I got E, that is identity. Then this M is the least integer such that A raised to M, I am getting E. That's why that least integer M is called as order of, it's called as order of A, that element A, and it is denoted by like this, the small circle, and this is A is equal to M. So order of A is equal to M, it means what? a raised to m is equal to e, and note that this m is the least integer, the smallest integer. You have to remember this is the smallest integer which will give uh, is equal to e. So this is something about order of element, right? Now let us start the proof of this application. So what is the application? Statement is if G is a finite group, that means the number of elements in G are finite, suppose n. So let proof, I am writing here proof, let order of G is equal to n, and order of A is also mentioning here. So let us supposing order of A is equal to m. And in this application, we have to show that this order of A divides order of G. So in the claim I am writing, claim to show that or to prove that order of A divides order of G, that is to show that order of A is m, so m divides n. So this is our final target, to show that m divides n, right? Now since order of A is equal to m, therefore we can write since order of A is equal to m, this implies A to the power m is equal to e identity, and m is the least integer, positive integer, least positive integer. Using this fact, we can construct a cyclic subgroup generated by this element A. So cyclic subgroup is denoted by like this. So let this symbol is denoted for cyclic be a cyclic subgroup generated by element A. All right. Now, since it is a cyclic subgroup, I can write this subgroup, elements of subgroup as A square, means A times A cube, and finally the order of A is m, therefore I am getting A to the power m is the last element of this subgroup. Right? Now, we know that A is a member of G, A square is a member of G, that means all are members of G, therefore this is a subset of G and it is a cyclic group, therefore I am calling this is a cyclic subgroup of G. So therefore this set is a cyclic subgroup of G. Now, can you guess that how many elements are in this cyclic group? All right, by observing index powers of A, we may say that the order of this cyclic subgroup is equal to m, because I am observing the powers 1, 2, 3 up to m. But we have to show it that it containing m elements. So now our next claim is to show that order of this cyclic subgroup is equal to m. To show this, assume that order of this cyclic subgroup is not equal to m. That is, order of the cyclic subgroup is equal to something less than or greater than m. So I am considering it is m minus 1. So that means in this list of these elements, some different powers of A gives the same answer. All right. So I am considering that different powers. So let I less than or greater than j and this j, I and j, that I is less than m. All right. So therefore, since the order of this cyclic subgroup is m minus 1, that means in this list any two elements having different powers gives the same answer, and these different powers I am supposing I and j. Okay, so I am supposing a to the power I is equal to a to the power j. Right, this is the element of G. G is a group, therefore the inverse of a to the power j must exist in G, and we take that inverse and operating both sides, we will get a to the power I minus j is equal to element and its inverse is giving identity. All right. Now, what is this power I minus j? And we know that the I is a number less than m when we are subtracting j from that I. Therefore, definitely I minus j is less than m. That means a number which is less than m, which has a power of a, giving the answer a. Oh my God. It is a violation of definition of order of A, because already we have assumed that order of A is equal to m and m is the least number. Then once we stated that order of A is equal to m, then m is the smallest integer, which give a to the power m is equal to e. Then no integer less than m become order of A. But here this j minus I minus j, which is less than m, becoming order. It is not possible. And therefore, this is not possible. It is contradiction. It is a contradiction. Why it is contradiction? Because order of A is equal to m. And m is the smallest integer, which give you a to the power m e. This is I minus j giving e, but I minus j is less than m. So it is not possible. And therefore, our assumption, what we assume that order of A is not equal to m. This assumption is wrong. So therefore, our assumption is wrong. So what will be the correct assumption? Correct assumption is we correct that order of this cyclic subgroup is equal to m. Now, this is a cyclic subgroup of G. Then we can use the Lagrange's theorem. So by Lagrange's theorem, what Lagrange's theorem stated? By Lagrange's theorem, the order of this cyclic subgroup must divides order of G. What is that order of A? Order of A, that is m divides n. All right, and this is the end of this application. So we have proved order of element of group G always divides order of the same group. All right. Now let us see the second application. Now read the statement. If G is a finite group and an element A belongs to G, then prove that A raised to order of G is nothing but equal to E. All right. So let us start the proof of this application. Read this. G is a finite group. That means it containing finite number of elements. So let order of G is equal to n. Now there is some element, and the element of finite group definitely possesses some order. So let order of that element A is equal to m. Right? Since order of element A is equal to m, therefore a to the power m is equal to e by definition of order of element, and where mentioned here m is the smallest or is the least integer. And let me call this expression is equation number 1. Now from the application 1 we know that order of any element of G divides order of G. That means m divides n. This implies n divided by m is equal to some positive integer, and it is denoted by k. Therefore, n is equal to m into k. All right. Now let me call this expression is an equation number 2. Now what we want to show that this equality a to the power order of G is equal to E. So let us consider, we are writing claim. Claim is to show that a to the power order of G is equal to E. Now consider LHS, left hand side, that is a to the power order of G. It is equal to a to the power, what is the order of G? That is n. So from equation 1, the value of n is equal to m into k. So using the laws of indices, I will write a to the power mk as a to the power m raised to k. And from the equation 1, the value of a raised to m is equal to e raised to k, and we know that identity raised to k is again identity, and therefore this is what? Right hand side. Hence we proved left side is equal to right side. That means a raised to order of G is equal to e. So this is the end of this application number 2, and we have proved this statement which is stated in application number 2. Thank you very much.